Okay, that's weird. So the clock on the podium is not the same clock as they're using for the recording time. So I'm getting a lot of questions about moment of inertia, and it just happens that this sort of falls in really well with a discussion I'd like to sort of introduce for the first time here. So you know that linear momentum in this course is g. And g, as you integrate over the entire mass, is just v dm, which at the end ends up being mvg. And all of this is a vector. Now, if I take a look at some arbitrary point on that body, and I look at, say, the center of mass, and I'm going to tend to focus on that, I can calculate its angular momentum. Now, the other thing I should mention here is that if you want to sort of look at an alternate derivation, you can look at section 7.7, which is not covered in MIE 100, but it's useful to sort of see some of the development of these equations. But they do it for three-dimensional motion. I'm just doing it for planar motion. H sub g is equal to the integral of r cross v dm. And you can say, look, hg is equal to the integral of m r cross omega cross r, and I'll get all the vectors, dm. And there we go. Recognize that A crossed with B crossed with C is equal to B A dotted with C minus C times A dotted with B. So I have an equation that A is R and C is R and omega is B. So I can start to put substitute back in. And if you do that, you end up with something else. H sub g is equal to omega times R dotted with R dm minus, and that's an integral on m, integrated on m, R times omega dotted with R dm. And you end up with H sub g is equal to, in a Cartesian system, x squared plus y squared plus z squared dm omega xi plus a whole bunch of terms, omega yj plus omega zk minus the integral over the mass of x omega x plus y omega y plus z omega z times the quantity dm x I plus y j plus z k. Lots of terms. And I'm going to talk about that table afterwards. I hope at this point in the course you know where table D4 is in the text and that it's a useful table that you should have for yourself. But unfortunately, it's sort of crowding my derivation right now. So if you do this, you can write H sub g is equal to the integral of the mass y squared plus z squared dm omega x, it's going to be a big term, minus the integral xy dm omega y minus the integral m xz dm omega z. And I'm just going to flip this around, so I just have to write one term, I plus integral over m of x squared plus z squared dm omega y minus integral of mass xy dm omega x. Oh, this is just m yz dm omega z. And that is in the j direction. Finally, over the mass, you have x squared plus y squared dm omega z minus the integral of xz dm omega z minus the integral of yz dm omega, omega x here, omega y, and all of that to k. All right, so that mess of terms is a fully three-dimensional motion and full three-dimensional rotation. And out of that, I'm going to end up with a set of terms. So I have a first set of terms that are x, y squared, z squared, x squared, z squared, x squared, y squared. I have the next ones, which are xy, xy, xz, yz, yz. So I can write those terms out sort of separately. Yeah. And I'll get a set of terms I could call the moment of inertia about the x, y, z axis. And one of the things that you should see right away out of this is it's an r squared dm term. So we're actually deriving that. We're getting to the point, not yet, but getting to the point where we have a length squared times the mass and integrated over the surface. And from that, we're going to get this moment of inertia. Everything else, the omegas are going to play a role, but they will play a role as a separate term that we calculate. So if you go further, you can say hgx is equal to ix omega x, ixy omega y, plus izx omega z. And hgy is equal to iy omega y plus ixy omega x plus iyz omega z, and hgz, which doesn't look like a z there. There we go. Excellent. Is iz omega z. Ix z I'm going to get this right. Omega z plus I z y omega z. So that's great. That kind of is a derived quantity. Ooh, it's a derived useful quantity that sort of tells me everything if I have three-dimensional motion. But I don't have three-dimensional motion in this course. In this course, the only type of rotation that's occurring is about the z-axis. Everything else is 0. It can't rotate into the board about the x-axis. It can't rotate about the y-axis into the board. It can only rotate about an axis normal to the board. So that translates to getting rid of all the right terms. Bump. Yeah, wait a second. Bump, 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 bump. All those terms okay. So in this course, we only really have 3 degrees of freedom. You have motion in the plane, so linear translation, x, y, so ux, uy, or a velocity in the xy direction, and rotational velocity about the z-axis, omega z. So in the end, what you have is really I, z, g, or well, ig, let's say it's just ig. I about the g-axis is the integral of the mass x squared plus y squared dm. And if you go a little bit further and recognize that that x squared and y squared, as we have done a number of times, is just r squared, you end up with your moment of inertia equation, which is good for this course. And I don't know why it's so thin. There we go. The main point to this exercise is to just sort of convince you, yes, you can derive the whole thing. Yes, it works out really nicely from angular momentum. And if you want more, you can look at section 7.7. But the other side to this is don't worry too much about the moment of inertia. Make sure that you know how to use it. So I'll do another example in a second. I just want to return to it. But I want to find my tables. There. Ah. There. There. Perfect. So table D4 in the text is really useful, and at this point you really should be spending time putting together that final exam crib sheet that you need to finish with. And let me just sort of zoom it out just a tiny bit more there. And here you have circular cylindrical shell. You have half cylindrical shell. You can see sort of the mr squareds. So those are hoops about the z-axis. You have circular cylinder, semi-cylinder, and we get both of these nice little half mr squared terms, and the 1/12 ml squared and the 1/3 ml squared. I'm going to derive the equations for the slender rod because I think it's still worthwhile. But But that's table D4. You have it. You have the whole text. All right. So another thing is, can you derive all of this stuff straight from first principles? Yes, you can derive it all from first principles. Here's a long, slender rod, and I have defined the origin at the center of mass, and the center of mass is given by that dashed red line. I is equal to the integral of r squared dm over the whole thing. Now I can define a density, and normally I would define a density as a mass over unit volume, but because it's a long slender rod, I don't really care. I don't know anything about the cross-sectional area. I'll just define it as mass per unit length. And if I do that, I can sort of look at it from, well, actually I don't even need the sigma there. So I can sort of say, hey, it's ml, but it's also dm dx because it's a uniform rod. It never changes in shape. It never changes in density. So delta is equal to dm dx. And x is just that distance across there. And I can also say m over L dx equals dm. So now I have something I can shove into the integral. So I have r squared, which is defined really as x, and I have dm, which is now m over L times dx. So if I do that, I can say I is equal to the integral of m over L x squared dx. If I do that, I can just substitute in m over L x cubed over 3 integrated. And here's where my first problem comes in. I've got to make sure I have the right integral values. I go from minus L over 2 to plus L over 2. So I'm going from the beginning to the end in this particular part of the problem. So it's minus L over 2 to L over 2. And I think well, I'll call it L over 2. So if I do that, I ends up being, oh, no, that's not the one. X cubed, right. M over L, and I shouldn't mess with my things, but 2L cubed over 24. And that will equal 1/12 ml squared. Okay. So setting up the integral, once you do it, it's okay. And that's just the dis method there. You also had another approach that you could use, which was, or another sort of extreme that you're used to, which is you pin it at one end. X equals 0 in that case is one end of the rod. The entire rod is length L. And you can do the same integral except you change the limits. So I equals the integral 0. I'm going to go to L, m over L, x squared dx. Substitute terms in, you end up with m over L, L cubed over 3, and you end up with your 1/3 ml squared. All of this you can derive. All of this is not worth deriving each time you do it. And it's really important to know sort of the fundamentals, well, the kind of kludges we've put into this. So if you have a mass of 3 kilograms and a length of 2 meters, you can calculate I sub g, and that will be 1/12 ml squared, 1 kilo per meter squared. I about an end is equal to 1/3 ml squared, which is going to end up being 4 kilos per meter squared. And okay, if you don't want to do it with the 1/3 ml squared, you can do I of the end as equal to Ig plus ml over 2 quantity squared, and not surprisingly, you get the same answer. And finally, you have the radius of gyration of this, and you end up with 0.5774. And what that means is that what you've done is you've taken this long, slender rod, and you said it's equal to a hoop. And that's a length of 2 meters, right? And this is a hoop of 0.57 meters. Take advantage of what we're giving you to solve problems quickly. You have tables. You have the standard sort of things that you must know. We will not tell you on the final exam 1/12 ml squared. I can tell you that right now. Parallel axis theorem. All of that you need to know in order to solve these problems. So if you're looking for something to focus on, make sure that you just focus on the idea of defining and knowing 1/12 ml squared for the center of mass of a rod, 1/2 mr squared for a disk, and finally a hoop mr squared. And if you do your homework at this point, you have enough problems looking at moments of inertia. It's really helpful to have that crib sheet next to you to sort of say, okay, yeah, that makes sense. I understand this. And that's one of the reasons why we really want you to start putting that crib sheet together much earlier. Okay, so the other things that you must know at this point are radius of gyration and parallel axis theorem. You really have to know those. You have to be able to be familiar with it. We will not help you with either of those if we give you information. So the other thing, too, that's really important is to recognize this is not anything more than a substitution for mass when you deal with rotating systems. So when I look at second law, sum of forces equals mass times acceleration. Sum of moments equals IG alpha. Now I already know alpha is only going to be k in this problem, and a will only be in the xy plane. And again, when you're dealing with rotational systems and translational systems, for kinetic energy, it's 1/2 mvg squared. And for a rotational system, it's 1/2 ig omega squared. Finally, and the stuff that we're most interested in, I'm not going to do that. Linear momentum is just mass times velocity of the center of mass. And angular momentum is IG omega. The first and third term are vector quantities. The second term is a scalar quantity. Questions? Really, the important point here is if you focus only on that and know how to do these equations and how to do these problems, you should be able to handle everything. You don't need to go back and rethink what moment of inertia is. You should not spend a lot of time other than to say, okay, I've got a slender rod, it's 1/12 ml squared. I've got a disk, it's 1/2 mr squared. Or, for example, there's a question 5 on the assignment. You're given the radius of gyration of a spool, knowing that that is going to be mr squared. Yeah, that's the one. Okay. I think I mentioned it, but I should re-mention it. This is the last lecture on Chapter 6. So we have completed pretty much everything. Tomorrow we will start vibration, and then we're 6 lectures from the end. Okay. So I have a spool, a disc that rolls without slip. It's its R is equal to 0.88 millimeters. Theta is equal to 24.204 degrees. Again, now that I can do whatever I want to with computer algebra, I just put weird numbers in because it comes out with nice numbers. You're asked to find the value, or what happens when the center of mass of this object reaches a velocity of 1.7 meters per second at t equals 2 seconds, and what is the radius of gyration? And again, recognize that notation so that you can sort of do all of that. That's why. Now, I wrote this problem this way, so I am going to keep to the notation that I used. Now, again, I'm expecting it to roll down the ramp. I expect to have a counterclockwise rotation, and normally if I were doing this from scratch so I don't have to remember it, I'd put the friction value flipped around. But it doesn't matter as long as you're consistent. So in this case, I know that I have a velocity problem. It starts from 0, goes to a final velocity, and it's a time problem. So mass velocity or force velocity time. And so I recognize right away that this is a momentum problem. Yeah. And just as a reminder, X and Y. So my linear momentum equation, I'm not really, I've got no bouncing of this object. It's not moving up and down relative to that y-axis, but it is moving up and down the ramp, so in the x direction. So VG1, VG2, all of that. And so that will be my equation 1. I also know that in this particular problem, which I have hidden everything from you, that weight is not causing a moment, normal is not causing a moment, but the friction is. And good for me, I'm keeping everything consistent with my order of rotation, and so counterclockwise is positive. I'm asked to solve for the radius of gyration, and so if I'm asked for the radius of gyration, I can write everything in terms of that. So I'll leave it as mkg squared. And everything is going to be relative to the center of mass. So Ig omega 1, Ig omega 2. I'm not going to take it about the point of contact. Now, again, to remain consistent with my notation, I need to sort of write this as a negative value. So omega 2 is negative VG2 divided by R. Essentially, I'm still doing a vector solution here, but I've sort of spread it out and basically solved it. So as before, and as yet Monday, and substituting in all the terms, I can relate these two together and get rid of my f delta or f dt integral. So if I get rid of the f dt integral, I have everything else that I know. VG2 I know. I don't know kg squared. or kg. So kg is equal to 1.7 meters, which is why you had that value of theta at the very beginning, which was 24.201 degrees. I can do that on in a lecture. I can't do that. Maybe we could do it on an exam. Any questions? You're going to, particularly in this last homework assignment that you're doing this weekend, you're going to see these terms. You're going to have to do this sort of analysis. So make sure that you are comfortable with this. And again, treating that moment of inertia just as it is, which is just an object that you kind of have to deal with for different cases. Nope. Hoop and bump. Oh, I like the hoop and bump. Okay, this is another kind of case where things are very, I mean, it looks like a really complex kind of motion, and you have to break it down, and once you do, it's not so bad. So I have a model pipe that is modeled the pipe as a uniform thin ring with mass m and radius r. What is the minimum d of the, so the pipe rolls over the step, and I think I forgot to tell you what d was in this. Yeah. D. So you have D here, and you have B here. So D is the height that this thing starts from. It's rolled down the ramp, and as it rolls, it reaches a final velocity. Then it continues rolling, and it sort of hits that bump, which has a height B. Okay. So it starts at 1, it ends up at 2. Let's do this. And so from 1 to 2, I'm going to do it here so I don't have to redraw it. T2 plus V2. So at the top, it starts with 0 velocity, but with gravitational potential of mgd. At the bottom, it has 0. But at the same time, it has a 0 potential. But, okay, let me just start writing things down instead of saying. And I'm going to define everything with respect to Q. Sorry, I should do that at the beginning, which is the point of contact with the ground. And why am I doing that? Yeah, that's a good question. Why am I doing that? Why about Q? What's special about Q? It's a point of contact. I have rolling without slip, and so that point has 0 velocity, but it has an angular velocity. So I can sort of say omega 1, omega 2, IQ. Okay, so everything has been transferred to that point, and I'm referencing everything to it. If you use the parallel axis theorem, you'll end up with IQ is equal to twice mass times r squared. And you know what? I'd encourage you to do that. And because I'm going to run out of space. Ew. So after it rolls down from the top to the bottom, it has its initial potential energy, which is mgd. It has its final kinetic energy, And the datum for this is, of course, the center of mass. So you have to do everything with respect to the center of mass. So you have the first sort of relationship between the initial position and the drop. You have sort of a relationship between d and omega 2. I really put these things too close. 2 to 3. Maybe I'm going to. So between 2 and 3, it moves. So this is just before impact and hitting this corner right here. And so between 2 and 3, it doesn't do anything. But over here, it hits this surface or this corner, and it goes up a distance, or it's going to hit, and there's an impact between the disk and point B, or height B. So that term, I could say, is HD3 minus equals HD3 plus. H, of course, being my angular momentum. There's no other forces playing a role. Yeah, good. Hmm? It's rolling without slip. What happens with rolling without slip? Yeah. So HD3 minus, HD3 plus, there we go, equals IG omega 3 plus. Let's see. 3 minus is equal to IG omega 3 minus M R minus B V3 plus, or minus, excuse me. So what I expect to have happen is it hits the corner, it has a translational velocity and a rotational velocity at the center of mass, and I'm going to sort of look at that. On the right-hand side, after impact, it's rotating. So I expect that what's going to happen is it hits the corner and starts to rotate about. It's not moving yet. It's not translating. So actually, I should. Okay. I'm going to call this point D, and I can substitute that in so I don't have to deal with anything. And so the difference is that IG is a hoop, mr squared. ID is at the point of contact. And I've already calculated from the parallel axis theorem that that's 2mr squared. So I have all of the answers that I got before because it just sort of rolled across. It's all good. Nothing happened. Nothing exciting. It just kept rolling along. So V3 is omega 2r, and I have to keep my sign. Omega 3 minus, these are before impact, omega 2, square root of GD negative over r. So did I call this an equation? No. I'll call it star. So if I go back to the starred equation, mr squared square root GD divided by r So it's going to go over the surface, and when it impacts against that surface, it's going to be, I can solve through minus square root GD over 2r squared times 2r minus b. Still variables, but it's okay. And now I wish I could just select it. Wait, maybe I can. Anyways, looking at this right here, I can say 3 plus to 4 I can say V3 plus is equal to 0. V4 is not equal to 0. MGB. Because the block or the hoop has gone up a distance b. So the center of mass has gone up a distance b. So V3, gravitational potential is 0. V4, gravitational potential is positive, MGB. T3 plus is 1/2 I d omega 3 plus, quantity squared. T4, on the other hand, I'm asked for the minimum height of d, which means T4 is equal to 0. That's the minimum for it to just go over. And so in terms of variables, and substituting in all the terms that you have, you get this. Questions? Go ahead.
Is the plus notation the moment after event?
Yeah, so it's after 3. So now what I've done, because it's problematic because they end up in the same position, so for position 1, and then somewhere in between 2 at the bottom of the ramp, from 2 to 3 just before impact, 3 just after impact, but there's no real motion. So the impact has occurred, it had translational velocity, then it has, or translational and rotational velocity, then it's only rotation about point D, and that's all I want. So that's where I'm going there. And then after impact, I have 3 plus, which is this value right here, and 4. And so that's where it all kind of goes together. Let's see where I'm at in terms of timing. I got about a minute. Okay. So really, I don't have time and I don't want to start a new example, and there's no point to it. Tomorrow we're going to start vibration, which means we're going from chapter 6. So we've covered all of 1 to 6 at this point. And the unfortunate thing about all these digital copies is that nobody actually sees how big the book is, but we've covered almost 600 some odd pages so far. It's very thick. And after this, we have another 100 pages, 7,500, on vibration. So there's a lot still left to cover, and this is a bit of a turnaround because we're going to approach things a little bit differently in the next 6 lectures than we have up till now. So we're going to go from force equals ma to force equals mx double dot. And I look forward to seeing you tomorrow.